Okay, so once again, we have started the recording, and we can slightly move to the first presentation.
Yeah.
Um, oh. Hmm. Okay. The question to our online friends, can you see the slides? Anybody there? I hope so. So, it's my great pleasure to welcome here first distinguished guest, Dr. Alan Cheng from Light Momentum Technology. It's one of the companies who are also involved in our ACDRC project, this quite nice collaborative project. And since Alan is quite skilled and expert in AI, I'm very happy to have you here, and the floor is yours.
Yeah. Really, I don't hurry up. And thank you, everyone. It's a great honor to be here. And I'm Alan Chen from Taiwan. I'm the CEO of Light Momentum Technology. At the same time, I'm an advisor of Taiwan Economic Affairs. So I suggestion for Taiwan government, we should be collaborate with our project partners. And the first, I think I should be send a gift to Professor Hazel. Please take a picture for us.
Okay, thank you very much.
Who can do it? Sorry.
I will.
Thank you.
This is the shape of the island.
Yeah. Oh, one more. Thank you.
Thank you very much.
Yeah.
So, Alan, floor is yours.
Yeah, it's my time. and thank you, everyone. I think we need to talk. When we talk about the practical application of AI and the customized chip in edge computing scenario, is a bigger issue. But in fact, the light momentum technology focus by this way. Our engineer team is excellent. Later GR will come in. So about technology problem, you can ask the GR, not me. I focus with for the business side. And in fact, the edge computing now is very popular. Everyone say we need edge computing. But the first question, what's edge? What is cloud? That's very important because in fact, ideally we can think about if with the data center, now we in the classroom, we are in the edge. But when in the classroom, we have the many equipment, AIoT equipment, the sensor, the detect something by thermal image or anything. That is cloud, that is edge, and we are stay in the building. We have a cloud computing power, so we need to know what we want to do. So in edge AI, custom silicon and deployment, we need to think about how to do it. And as I said, I need an introduction about light momentum technology first. Thank you, Professor Hannah. I have another gift for you. Which we give you this. The chip-based intelligence we built up in 2021. And at the time, in fact, we don't think about too much for IC design because IC design at the moment is very difficult job because main China right now, the cost, the human resource cost is very low. The one Taiwan engineer, they can hire 3. So at the moment, we think the IC design is too difficult for us. But luckily, we have a war. We have a President Trump, so we have opportunity again. So almost 2 years before, we rebuild up the IC design team and rely on our CTO GR. Like I said, later GR will come in. He is a real engineer. He is work very hard and always fly to everywhere, more than me. He will think about which payroll is the best for your trip. So he's an engineer thinking. And in Taiwan, now our business, we have a different business, but for edge AI application, for the physical AI device, is we focus. So we can do it. And before I talk to more about the topic, I think I can introduce you why Taiwan is suitable for IC design company. I'm the advisor of economic affairs, right? And Taiwan have many strengths for IC design company. The first is distance. We are short distance to the fab. We can easily to connect to TSMC, UMC, TSMC, and the other more. And the communication become very easy. Maybe everyone will think we can find the agent. They are the TSMC agent and they can support us. But in fact, if your communication need to pass the message, that is difficult because semiconductor is very detailed and the many things you should be care about. And easily to connect with TSMC, not only by the distance, by physical distance. Another way is by the mindset. Like we have a joke now in the United States. The TSMC in United States, Arizona, Phoenix City, and the local employee, they think the TSMC people is so bad. Why? The TSMC engineer from Taiwan, if in a meeting, morning health, they will speak Mandarin and they don't use English. So the United States employee feel very angry. And it's become a bigger problem because for TSMC internal, we can use Mandarin communication. It's very soon, easily. We can directly talk with which thing, how happened, and by which command we need to do something from Taiwan. So the real distance, not from the physical, it's between the culture, between language, between many things. So Taiwan is easy for IC design because we have fab. It's a real reason. But for Czech, now we have an opportunity because next year, the ESMC will open in July. And the ESMC will have a more Europe employee, local hire. So we can communication more directly. And you can easily to make sure what you want to do is suitable and easy of the cost. So you will feel more easy. And the second, in Taiwan, we have a shuttle model. What's shuttle? Shuttle means like we have a 10 research team from different university, from different stars. And then we need we know you want to make the real chip, you need a mask, it's right. And the mask cost is higher. And the one time maybe you will lose, so you will lose all of. So the chip is useless. But if in Taiwan, we have a shuttle model. Shuttle model means take together 10 companies integrated together, or 10 research team integrated together, become one shuttle to communication with the fab. And then the cost just need 10%. It's right. In original, you need for by yourself to ever all of the thing. And then in Taiwan, the 10 research team can use the same mask and to do the chip at the same time. So the cost is very low. So in Taiwan, if you have idea, you want to make a real test chip for your customer, it's easy. And we know that the end customer, they don't care about too much. They will say, I want the real chip I can test. Don't tell me you can simulation. So simulation is good, but we still need a physical chip. And in Taiwan, it's easy. Why I talk about it? Because now we have an ACDRC program, right? And we can collaborate. If you have any great idea, great algorithm, you want to become a real chip, can collaborate with Taiwan. And you can tell me, and I will try for you to have a real chip. And then you have a real chip, you can advance with your customer and get the real results. And this is our core team. I'm Alan Zheng. This is me. I'm Alan Zheng. Now I'm still doctoral candidate. So doctor is still have a that smile for me. It's very difficult thing. And in fact, in original, I give up the engineer job for a long time. I become a banker for a long time because the banker salary is higher. So at the moment I become a banker. But at the last, my school senior GR and the other our team member asked me come back because they say engineer still need business support. So I come back and included the funding and many things. Yeah. And then is our general manager Tommy. Tommy in before he worked for like a Siemens and many IC design company. The GR is CTO. He worked for ARM before and Umbrella, and KC is worked for Morningstar in before, and the last is Low Jihan. Sorry, his Chinese name is Jihan. He's for AI algorithm. So you see, our team, you need a software, you need hardware, you need a chip designer, and then you need the financial support, and then you will become a company. So I think it's a good team. We work very smooth, and each other is very similar with each other. Yeah. And our core product, we have three main business. The first is IC design. Of course, IT design is our main business. And now we have a Singapore customer, we have a Europe customer, like Codasip have a little project for us. Because our team in origin, like I say, is from ARM is right, and ARM is risk-based. So we can do for them. And this year we will have a second program with them. I think so. So we will keep collaborate with Codasip. And I have a suggestion for them. Maybe this year we will apply Sigma program together. Yeah. And now in IC design business have two different parts. One is for SIP, for IP design, and the IP is offered for our partner. They are the company. They want to make the real chip because the make chip is still very expensive, especially for advanced chip. So we will collaborate with different IP and they will integrate it, or we will integrate it for them. And another business is make a real chip. Usually it's more simple one. Like in Japan, we ever have an interesting project. In Japan, the people very like pachinko. Pachinko is a gambling game, and the pachinko machine need a chip. And then make the pachinko chip is easy to earn. So maybe it's a good thing, but it's another good project because it's gambling. So in usual we will announcement too much. We will not announcement too much. And the second for AI application, like AIoT integrated. If we only have a chip, the customer could not use because they still need a PCB board, they still need a modularization, they still need a sensor integrated. So in fact, in Taiwan, we have a team in Taichung. We are integrated for customer, and then we will have a test module. That's important because test module for customer, they can real test and to know the effect and the performance. So we will do more advanced for customer. I think not only for the startups like our company will do it, even like a bigger company like MediaTek or others, they still have the module team. The module team will do the real device and the test for them, for customer to test. And another one is AI chip integration with device. This is just like I say, we have a chip and we need to have a device and we need to integrate it together. And this is another strength with Taiwan because we know Taiwan for electronic manufacturer is very strong. And we have many not so big company like in Czech we know Wistron, Fastcom, Inventec, but sorry they are too big enough. They just want the project can make a huge balloon. So if you talk with them, I want the customization with something, they will not do it. But in Taiwan, we have many small startups. The company is make more flexible. they can maybe 10 devices they can manufacture for you. So that's easily for us. So this is another strength for Taiwan. And we can integrate it for customer because maybe the chip is designed by us. And then we can collaborate with our Taiwan partner and become a full device for customer, for end customer. And third is for fintech. Fintech is another thing. At least last year, Martin and Mohita come to Taiwan. Thank you for you all. We have we in January, right? In January, and we eat a annual party and join together. It's very happy because in Taiwan, the security trading you need by the advanced equipment now. Oh, the trading now is immediately, maybe by microsecond speed. And the microsecond speed, if you use traditional server, is very difficult. So in Taiwan, we based on our strengths, we support the securities exchange to make the high speed or overclocking server and the FPGA solution for them. Because the application, the volume is very small, but the value is high, so they will pay for us. So we have a business by this way. And we have two products. First is overclocking server and the Smart. The speed maybe in usual we can make the one transaction in 10 to 20 microseconds. 10 to 20. If sometimes it will be a little better, but in usual it's 10 to 20. And if the engineer team not so expert by this way, maybe the same machine they just can use it, just can make it maybe 30 to 50 microseconds. So it's a huge difference. It means your competitor is already complete their transaction, but you still in process. So we make a business by this way in Taiwan. And now in Singapore, have a customer just test. And another one is for FPGA. So you see, from FPGA to the ASIC, MCU, SoC, we all have experience. And we can, based on customer situation, to support them. And if anyone have an interest for high frequency trading, we can have an advanced discussion. And that's very interesting for me. And Europe is more popular, I think so. Have many exchange, they can use high frequency trading to make business. So the local demand is strong. 2024, we already landed in Czech, and we registered our company in Praha because our partner in CTU, not in Brno. And at the moment, I need to thank you for Mr. Ochiko. He's a so great man. Yeah. And in original this time I visited Czech, we will have a dinner, but it's a little uncomfortable. So we could not meet with each other. We need them in May. May we will have the Czech Semicon Days and welcome everyone. I forget to introduce my another role. I'm the Secretary General of Taiwan Eastbound Alliance. The Taiwan Eastbound Alliance is an alliance. It's an NGO support the Taiwan semiconductor and the technology supply chain from Taiwan to global. So I have three roles: the CEO of Light Momentum Technology, second, the advisor of Taiwan Economic Affairs, third, the Secretary General of Taiwan Eastbound Alliance. And this year in Czech Semicon Days, we collaborated with Czech investor. The Czech investor, they are very positive to promote Taiwan semiconductor supply chain to lending. And this year we have many good news. We collaborated for a long time, almost 3 years. And this year have a Taiwan company for semiconductor chemical and gas. Then we are landing in Usti. And then we will build up storage and produce line in the later in Usti area. And collaborate with the local university to test, to certificate for the quality of the chemical and the gas. So it will be a great thing in nearby Dresden, and they can support all of the Taiwan supply chain to make sure the quality and the product standard is suitable for TSMC. And it will be a big investment because the local university say they will apply the EU program to support to build up everything, the equipment, the test machine. So there will be a big invest. And the company is our member. And not only the company, we still have the power chip company, have the market tech for equipment and the process for TSMC. And the other Taiwan company will opening in at the same time. So welcome everyone to join the Czech Semicon Test in May. It will be a big party, yeah. And now we need to talk back to our focus. We offer custom, reliable computing solutions. In fact, we don't talk about, we just only offer you cheaper solution. The cheaper solution means we need to make a ASIC, MCU, SoC, but in fact, in usual not. We will give a customer the suitable computing solution. Yeah, it's still solution. And we know computing is everywhere. And the reliability is the required. The different things like IoT, like cloud computing, edge computing, AI, automation, everything. Now you think about, we need a more smart, have a more intelligent. But how to do it? We need the computing power. And the computing power should be from some silicon by general purpose chip for FPGA, for like we just talk about the ASIC, MCU, SoC. So, but if you use each kind of the silicon, we still need to make sure the quality, security, safety, and the controllability, everything is needed. Like our partner, Professor Hana, their team is an expert by security and safety. I remember for a long time. And I think this year we will have more project can collaborate because now we have some project and they need a high security and high safety. So we can make sure our customer, their product, their end product, their chip, what we design, we are suitable for EU standard. Oh, that's important. We need to make sure it's suitable for the standard. And this topic now is a matter very important. It's very important now. The market is no longer asking only for more AI compute. The Jensen Huang is become the rich guy in the world, and NVIDIA is the biggest market value in the world. But they already make too much. In fact, the general purpose computing like a GPU is not suitable for all. We all know it. We all know it. In many edge scenario, we could not use general purpose chip because the thermal issue, the power efficiency issue, is all very important. And the general purpose chip, there will be a huge waste. Why? Because general purpose means they need to everything. And in fact, you don't need everything. You just need to do one thing and one process. And why you need a so huge chip and the high cost. So now we need to think about the deployment in the real bottleneck. By the scenario, which we think is the most important, we need to think about. And the cloud is changing too. In fact, in original, we want to build up the LLM model, so we need a GPU. But now, we already become for application is right. And for application, we know the algorithm is more clarified and more fixed than before. So feasible than before. So we can use more focused chip like Google do it. And that will be better because the power efficiency and the cost will be down very much. So many people say Google will win the war at the last, the chip war in the last. Maybe. Because NVIDIA, they are still very positive, so they buy and grow. And customized silicon is moving upstream. The many things, the bottleneck maybe for the communication, maybe for the workload, we need to know the specific for detail, and then we can do. The market is single, the market signal is strong. For edge computing, now like a drone, the many people now they want to do for defense, for military. because this area they need the single system without influence for many other issues. So they need the unique edge computing module for them. That's a bigger opportunity for everyone, like especially in Europe side, because the nearby and we know what they want, so they will be easily to do. Like Taiwan, Taiwan now is difficult to design the full drone because Taiwan have no scenario can use. We just use it to take a picture, to take a video. But in Europe, the nearby area, the people every day think about how to use it to become better. So it's a different situation. In Europe, I think the full design thinking of the edge scenario is better than Taiwan. Taiwan in usual, we just expert by manufacturer. So the design is by United States, design is by EU, but the manufacturer with Taiwan. And the Taiwan is a loyal partner because if you collaborate with main China, and then they will make their own device and better than you. Cost is lower than you, so you will lose again. But in Taiwan, we always just offer the product for our customer and their brand. The best example is like AMD. AMD and NVIDIA all the same. Now they don't have any fab. They don't make the dual chip. It's all from Taiwan, right? But the brand, the product, it still belong AMD, still belong NVIDIA. No one doubled with it. So collaborate with Taiwan, you will have a cost, the performance, the strength, and then you can make your business, your product for future, for more huge opportunity. Okay. And customized silicon matters both edge and the cloud. Just like I said, now even in the data center, the people will think about the customized chip for some application. Like your scenario is for ultra low latency, so your communication bandwidth should be very, 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 very huge, and then you will think about how to do it, and then maybe by the silicon optical, maybe. So you need from your purpose and the design and what you need to do and the real bottleneck, and then you will get your unique product and the unique scenario, and you will have your own business and have your success. So by different situation, maybe for GPU, for customized chip, or maybe for FPGA, all okay. So even in edge or in the cloud, it's all the same. And the edge AI is really changing many things. We need to care about latencies first, because many scenarios we need ultra low latency, not only for financial trading, like a drone. At the same time, your enemy will have more than hundreds, thousands drone fly to your country. And how to do? You need a huge computing power, and to make sure you control each device can defend. So why United States built up so huge capacity in Virginia? You know, in the world, almost more than 30% AI data center in the same area. The Virginia North, Virginia nearby Washington D.C., and the United States, the federal government, all in this area. So they need the defense, they need the auto system. So they build up so many huge data centers for it, and even with the nuclear power. So the data volume is not become very huge, and immediately, because when the drone fly, you detect with it, you maybe have less than 3 seconds, and then you need a judgment with it. Is which one can by which defense can really to resist with it. So I think the latency now become very important. But not only for this, like automobile, your car have something, the emergency, and you need immediately make a decision right. So on the car, the computing power, computing capacity need to become better and better than now. And now I must say, the cost will be very important. Like now, the EV car, the electronic cost is more than 40 and 50%, even 50%. The electronic equipment occupied all the budget for the car, more than 50, I think so, including the battery system. So the latency is very important. And second is power. Like the same in automobile scenario, your battery is limited. And if your computing is a waste of power, you cannot drive too far away. Your car every 10 miles need a charger again. So we need to make sure the power in edge scenario is important. Third, data movement. Sometimes we need to keep the security and the safety reason, or by personal private reason. We could not use the device. We will transfer all of the raw data. So we need to use edge computing to detect the results and just transfer the results to the cloud. And then your privacy and everything can keep it in edge side. So this is different. Like thermal imaging is another interesting issue, because if we use the traditional camera to take a picture with everyone, you will know this guy is who. But if we use the thermal imaging, we can detect who coming and what happened. But we don't know who is the real guy. We just know someone coming. So thermal imaging now is very useful. But the cost is a problem, because the thermal imaging cost is still very high, especially for the high quality thermal image. And safety and the privacy, yeah. So it's the same issue, just like I said. So you see, every different scenario, automobile is very important. So we always talk about automobile. But automobile now, because in EU, the main player in the automobile market is very weak. So the new product, new innovation is difficult to talk with them. They just hope can cost down and can survive. So we need to think about something is by better cost and high performance for them. So the same, you see the economic issue is always an issue. And for the engineering view, the edge first AI optimized for safe, for local response, for with cloud first is a different scenario. And the same, we need to consider the constraints with the real demand. And this is for the which AI task we should run in which different device, in different situation, like a sensor. Now we know the multi-sensor is a huge trend, because only one sensor is difficult to make everything well. Like Tesla is a good example. Tesla, they always say they just use, like people use vision to do everything. But in fact, only normal camera vision is not enough, because like a rainy day, huge rainy day, the cloudy day, many different scenarios, you will feel difficult in deeply night. So we still need more different sensor for it, like LiDAR, like the thermal imaging. It's everything we can need integrated with each other. Like in AI robotics, we need to think about which sensor they need. So the multi-sensor situation, we need a very unusual. We need a low latency with it, ultra low latency with it, and we need more edge computing power can bigger than original. And second, for some checking or pushing, we can use a little more time, 10 to 50 microseconds, and it's based on your purpose. Like in Taiwan, we have a national internet center. They are data center. They are belong Taiwan government, and one team in the center, they research for CCD. The CCD means the tracking system with the different sensor. Like we have many different camera. We have many different sensor with voice, with temperature, with other things. But by the system, they can check it, which scene or which people they go through by this way, and all the way go to which place. So the system, maybe in June, the team will from Taiwan to Europe, they will visit Poland and check. I think so. So if we have an interest for the checking system, we can have an opportunity to collaborate with them. And yeah, I have a new position with them. I become the advisor with the Taiwan National Internet Center. And then I think in different scenario, we have a different demand for different latency, and the preferred location in each place is different. But because later I have the real case can show, so I don't talk too much. You can see it. Yeah, the customized silicon is have a different choice, just like we say about the FPGA or ASIC or AI MCU or by SoC, NPU, or at least by cloud computing power. Is a different scenario. And in original, the people will think about cloud is good. Many people promote cloud and 5G. But in fact, until now, you have a new smartphone. But your internet speed have a really upgrade or not? It's a bigger issue. Everyone's talk about 5G is good, but in fact, by your experience, you feel differentness. So we need to think about the real demand, not we manufacture for manufacture. This is not a good way. We do something for do something. It's not a good way. And how to choose the silicon path? I think I list some different situation, different scenario for what you need. And I think I will not one by one to introduce with it. But I think we can talk about the okay, for the workload is stable and the volume is meaningful. The situation is you in usual the edge computing chip. The most important problem is cost. In Taiwan, we have a project, a motorcycle company. They hope their motorcycle can have AI function. Oh, it's difficult, it's right. The motorcycle, the size is small, the price is lower, and then you need to give them. If you use the automobile by the real car, the device is huge, the cost is higher. They could not use it. Maybe your motorcycle just 100,000 Czech crown, and the module is 50,000 Czech crown. So it will not make sense. So we need to consider it in this scenario. We need to consider it how to make the chip just enough to use. What is just enough? Your upgrade be limit. The performance, the task should be limited for low level, but the performance is still enough to be used. And then based on it, we can design the chip by which process, like the 28 or by the different. We could not use the advanced process to manufacture it because it's too expensive. So it's a different scenario. But at the same moment, we have a totally different situation with the drone. Everyone know the drone, the most strong company is DJI. It's right, DJI in main China. The people buy it because it's cheaper and better. Why DJI is cheaper and better? Because DJI have many unique ASIC only by themselves. And that's the problem. In the beginning, every drone company, they don't have a so huge order. Is right. Your demand is small. Why they can manufacture by ASIC, customized ASIC? Because their most important customer is a main China government. And the escalate, I hope, can get a better one. The cost we will pay. So if your customer, they will pay for all. you can deny better for them. We can use advanced process and make a real good chip. The performance higher and the power efficiency good, and the advanced process. But in normally, in general business model, you could not have enough capacity for everything you have. You need to choose something. It's the bottleneck. It's the key factor for you. Yeah, this is strong. We already see it. In drum we already see some situation. First, in original, people will think about the drum will have a central computing module. Each sensor connected to the central computing, and everything processed in the central computing. But in fact, now we see the new trend is for edge computing with sensor. Each sensor, like I said, each sensor they can have a low data and then have an AI function to judgment, which is important, and the key information will pass to the central computing module, and then each sensor they combine the data and the work payload is better than original situation. Because if we rely on the central computing module with drum, sometimes the scenario is we need immediately or the better performance or thermal management. So even in the drum, we still have edge and the central. It's right. So by this way, we can think about the vision sensor will be integrated with computing module and become a subsystem with drum. And each drum they can choose by which size or which spec with the edge sensing computing module. And that will be easy because the drum company they only just can decide for the drum itself, and then we can choose different computing the module can use, and you optimize your AI algorithm become easy because the data volume is become small and the latency become better. So I think it's a new trend for edge computing now. It's very important because we have a project in Taiwan. Taiwan have a very famous the company. Their name is Pizza Art. Pizza Art is for the vision chip company, and they have a traditional camera chip. Now they want to develop a high quality advanced thermal imaging chip, and the project we will integrate these two things, and on one device, and with AI computing module, and then we can settle down on the rubber dog or on the drum, and everything can use it. So in Taiwan now, we just have a project with it, and the rubber dog have the AI imaging module. They can by security check, they can do many things, like on the mountain to find someone have a dangerous. So it's a different scenario. Not all for military. I think for military just one part. After war, we still need a life. That's right. The good life, the better life for the future. So we need to come back to know who is the real demand, the real inquiry for the human's future. And like this one, we have a great idea. Which idea? Usually, if the cow have some sick, maybe they have a fever, maybe they have some virus, have a problem. But in usual, it will be have all the farm, the cow have a sick, and you will find. Because you could not every day to detect the temperature with cow. Is right. If the drum or our device can every day fly the cow, and to detect the cow is normal or have a dangerous, and the car will like better. Because in original, you know how to detect the temperature with car. The doctor will do something very, very cool, but I don't want to do it. So the drone with AI thermal imaging sensor and to detect the farm, the cow, the animal have something. It's a good check. It's a good idea. So we have a project in Taiwan with the first. Later I will introduce you for it. But now we just complete finish the first stage. The second stage now just begin to integrate everything on it. The AI MCU and the AI SoC are not the same job. These two things is a little different by different purpose, by different scenario. So we still need to think about like we already talked many times, the real inquiry or limit with the scenario, so we can make sure which one is you need, and by different situation. By software platform, if you want the more flexible, maybe SoC will be better because you can optimize for a long time. But if your application is like a more clarified, and you can have the AI MCU, that will be more easy, and the safety will be better. The power and the thermal decided whether AI can ship. In a different computer mode, we need to consider how many TOPS we need. That's very important because if you need a huge TOPS, the cost will be very high, and the scenario is totally different. And usually in original, I say the situation in Taiwan. The Taiwan government, the economic affair, we have a SESB for the company who want to develop the advanced drone chip, the UAV chip. But in original, the people think the government officer think about, if we want to have a SESB to the company, they should be do the advanced chip, the better chip. So they have a limit for you need a high TOPS, and then you can apply the project. But by real situation in drone, you don't need so huge high TOPS. You just need enough for use. Is right. So the limiter for the project is loose. Their purpose not success. So second year, we changed the rules, more focused with the real scenario, and the application can make sure it's useful, better than original one. So this is a good example for we talk in the beginning until now. We always talk about the real demand, the real limiter, is what you need to do and choose which type of the customized silicon for you. This I already talked about too much. The automobile is the best entry case, yeah. And this one, yeah, I already talked about it. And this one is the same. Yeah, this page is good because our time is very hurry up now. The NVIDIA and the Grok, they have a licensing deal, and it's almost the most expensive licensing deal in the world. Almost, it's a very huge amount of investor. Why they need to do it? Because just like I said, only GPU now is not enough. The cost is too high, and the power waste is too much. In the world, everywhere now people say, without enough energy, without enough AI. If every AI application, you need the computing, and the computing need the electronic power supply. So in United States now, very interesting. You build up a new AI data center, and then you need to build up the new power plant nearby. Because in original, the power grid is difficult to ever so huge demand. So in the moment now in United States, build up a power plant is more popular than AI center. So it's interesting. So NVIDIA knows it. of course, NVIDIA knows it, but NVIDIA will think about how to do for the future. So they buy they get the licensing from Grok and buy the CEO of Grok. So the Grok CEO now will become the employee of NVIDIA. But Grok still exists because still have many other customers. So it's a very interesting thing. And we can think about in the future, NVIDIA will have a more customer relationship. This is another trend point. And why is the meaningful industrial collaboration? That's important. In fact, this page is almost the most important page of my speech. Why I talk about it? Because in the beginning, we know the scenario decided the which type of chip, decided the which limit and the constraints. But what is scenario? The scenario means the real end customer demand is right. The people need it. Why people need it? Because the original chip, the original product could not use or not enough better for them. So they need a new one. That's the best reason for customer relationship. The customer chip, we always think about, we want to do something better than others. This is product thinking. But in fact, not product thinking. We need by customized thinking. The customer need. So in Europe, like we talk about the industrial collaboration, like an automobile company, they are nearby Czech. They are landing in Czech for 30 years. We know the demand for them. We can communication with the high-level manager with the automobile company easily. So we need to talk with them. What you want? What can help you? And we can do. In fact, I think all of my Czech friends is all expert. They are you are so cute and expert by the technology. But how to make business? We need to collaborate with your partner, the industrial partner, because the real scenario in their world, not our world. We are engineers, but the real scenarios in their situation. So we need to serve with them. We become the solution provider with them. Like in usual, I will not introduction for LMT for our company. Like Momentum Technology is a IC design company. We are not a pure IC design company. We are solution provider for computing. That's different because we will based on customer situation for the scenario and the service with them. So I'm CEO. I always try to find more demand with different industry and try to collaborate with them. Just it. So this page is important. We need to try. We need to try to communication with the real industry guy, and they will know what they need, and then we can do for them. It's right. Like I remember Martin and Boina come to Taiwan, and we visit. We hope can visit with Taiwan the rail companies, right? Yeah. If in the rail company you have some demand, you need to do something, but you have some limit, like the cost limit, like the power limit. So we need to think about what device and what chip can help you, and then we have a second stage to design for them. So I think we can have a more collaborate with Czech and Taiwan, because if we collaborate with each other, we can have a more advanced the strengths with others. Like the German guy, they are more. We don't talk about too much with it. Okay, the Czech people I think is better. We can collaborate with Taiwan very friendly, easily, and we have the same idea with beer. Sorry. So I think it's a good thing. And this is for the Trump for the real case. In fact, in this picture, I sit here. I'm here, but this time I don't show myself with the card. And why custom chip matter at the edge. We have a different rhythm by practical problem, by single idea. The single idea is about it. This form we need to think about the edge AI is where the theory meets dust, the weather, the battery limit, and the delay. So in different scenario, we will use it. And this is what we do, like we say the stage 1, stage 2, stage 3, stage 4 for real project. Usually, we will use embedded system for customer because now we need to test. We need to make sure the problem is really problem. Maybe customer will tell you, oh, Houston, we have a problem. But in fact not. In fact not. The customer, by their visit, they just know the problem is a problem. But for the real engineer, for the IC design engineer, it's different. Our problem is different with them. So we need for the embedded system to make sure the problem is problem. Second, integrated with AI edge system. Because in original we can use the central computing equipment like a server, like a cloud computing power. But if you want to become a real situation in the farm, in the far away place, on the high different situation, we need to think about the edge system, how to build up the inside. And the third, the customized chip path, how to make it. You need to make sure the phone. You need to make sure the everything. And the last, just manufacture business. So if we want to make a edge computing chip, we still by different stage, and then we can make it real. This is for drum. I think I already introduced with it. Once the payload latency, thermals, and the radio links, and all the same equation. We need to think about how many things should be on it. Like this one is a real project. This drum is belong to the Taiwan company, and we supported by the three optical module, and then the computing system by this project is still in the central computing chip in the drum, but the performance is very bad. Maybe they fly 10 minutes, they need to come back. So it's not a success. And this one is a more like a Ukraine situation. But by this way, this is the bigger one. The big drum and the small drum is different. The purpose we know is right. The bigger one, they may be by control function, by connection, by detect with a control center. So their design, their equipment on it is different. The battery size is different. So it's good. But for another situation, it's not like this. And this is, I just say like the cow. What we do, we need to make sure the ear, the nose, the ice hole, and the bottle hole, and you can make sure the multi target to detect with the cow, because sometimes the cow in the warm day will feel so hot, but not really cow have a fever, and we need to use a very high quality thermal imaging in the COVID-19. I think everyone ever used the detect module, the thermal module, to detect you have a fever or not. And we know it's not useful because if you are too hot, you need to cool down later. And you can go through the way. But by cow, you need to really to know his fever have a fever or not. So we need to use high quality thermal imaging to actually to catch the right place, and then you can get the result. But the limit, I think, is still the same issue. In original, the high quality thermal imaging module is very expensive. Like this time we use the module, it basically need 100,000 Czech crown. The thermal module, only thermal module. The full equipment, I think, total equipment by our project need maybe 500,000 Czech crown. But how much fund can buy it? how much a farm can buy it, the farmer could not buy it. So we need a cost down. And this is stage one, just like I said, the AI model and the embedded system. And then the second stage, we will serve the bottleneck with a chip label, because if we can use customized chip, the total cost will be down. Almost, we evaluate is a 20% of all the cost, because we don't use the so high quality thermal imaging. We can become suitable. Everything is just suitable. So it's just like in the beginning we said, just suitable for the scenario, and the cost, the performance, everything is better. And this is good product. You can sell to world everywhere. Like this module, you see everywhere in the world, everywhere have a farm with many cows. Every farm should be buy it. And if your cost is perfect enough, the customer will buy so much module for you, maybe 5 million. The million module, one module for 100,000 Czech crown is still huge volume, is right. The company will become very expert by this way. And that's only cow. We still have a pig and the lamb and the sheep, sorry. So it still have many things to do. And so thank you everyone. I think I only have the last minute. So the conclusion is we need cloud is great, but the cost do not wait for the cloud. We still need to have more choice, more solution for our customer and the scenarios. So thank you everyone. It's my speech. Thank you.
Thank you very much for your lecture. One short question, if we do have, then we, of course, have plenty of time during the lunchtime, but do we have one question right now? No?
Yeah.
Alan, just AI is quite important topic right now.
Yeah.
And in future, of course, once again. But it is quite energy demanding stuff. Is there any solution? No. I don't think so.
Yeah, I don't think so. Yeah. The same. Because in the real world, we have many, like we just talk about the limit, or by the real inquiry is different for different purpose. So the AI, the LLM module, or the general purpose AI is still too far away. I must say, too far away. Like AI rubber, many people say, like Elon Musk say, 3 to 5 years, everyone will have one. Every family will have one. But in fact, it's too difficult, even cost and many things. Like Taiwan have a very famous IC design company, the Realtek. Maybe you ever hear about it. The Realtek, they offer more than 20 chips for Elon Musk. But they say they have a big problem. Now they need to research for the material and can optimize their product become better. So now the Realtek have a new research team for material. So just like Professor Hassan said, not only one way can become better in future. Not only one AI can do it. Not only one chip can do everything. Yeah. Thank you.
Okay, thank you. I think we have plenty of time to talk about it later on. And now I see remotely connected another distinguished guest. Andy, hello, can you hear us?
Yes, Professor Hayes, how are you?
Wow, good.
Good.
So I will switch I see.
All right, wonderful.
So Now we will proceed with Professor Andy Chen from the National Central University, another colleague of mine who is dealing with AI stuff, but not just only this one, but also EDA tools and many others, as far as I know. And is that right? I hope so.
Yeah.
And he's going to give us his lecture on AI and his point of view on this problem. So, Andy, very happy to have you here, even though just only remotely. And floor is yours.
I just say hello, Mr. President.
Yeah. Hello, everyone. And I'm very sorry that due to my family issue, I'm not able to physically attend the AI workshop. But it's very appreciate the kindness from Professor Hayes. Still invite me to remotely to share some of our recent research results. And the topic I'm going to share today is AI-driven early routing, design rule check prediction, and the condition-aware pin assignment for faster physical design closure. So in this talk, actually, we will discuss a little bit more technical part on how the AI can help the EDA tool development. And as I just hear, the previous talk is very insightful and very interesting to see how the AI can impact our world. But for the IC design part, especially for EDA part, recently we have so many corresponding researchers that targeted on using AI to do the EDA related research. And in today's talk, I will be very happy to share some of our recent results here. So hopefully you can see my screen very well and hear my voice clearly. So during the presentation, if you have any questions or it's suddenly interrupted, just let me know. So I will try my best to reconnect it again. All right, so quickly introduce myself. My name is Andy Chen, and in Chinese is Chen Yuguang. Yeah, and I was get my PhD degree from National Tsinghua University, Taiwan in 2016, and I have a couple of employment experience in the St. Kitts and Nevis and United States, and also the Taiwan schools. And currently, I'm associate professor at the Department of EE at NCU and also a chair of interdisciplinary of EE and CS. And for my research interest, majorly focus on electronic design automation. And with the ACDRC project, we are very happy that we can continue this research with Professor Jacovinko at CTU. And also, I'm very happy to join this ACDRC workshop. And for the detailed research part, I majorly work on two parts. The first one is circuit reliability issues, and we emphasize on agent detection, mitigation, and the tolerance. And we consider from the transistor level all the way up to system level. So we consider agent-aware computing memory structure design, path design for hardware security, escalator design, so on and so forth. And also I use machine learning based methods to predict the circuit agent situation. And on the other side, we also work a lot with machine learning for physical design, from the partitioning, floor plan, placement, routing, design rule violation checking, and LBS, so on and so forth. And in today, I will introduce two of our recent works. One is using machine learning for design rule check violation prediction, and the other one is a pin assignment for a single block. And the outline of today's talk is as follows. First of all, I will just use like 5 minutes to give a big picture about modern EDA and why machine learning is very popular in EDA, following by the design rule check violation prediction work. And then we consider about the pin assignment work. And if we still have time, I will also share some of other machine learning for EDA works from my group. So let's start. What is the challenge in modern EDA and why machine learning is very popular for EDA? So as you know that until nowadays, for the entire IC developed technology was still following the Moore's law, where the transistor number will double in probably 18 to 24 months. So it means that we have exponential chip complexity like this way all the way up. And now we have much complicated design considerations compared to the good old days. So usually we only consider about the PPA, right? The performance, area, power. But nowadays we have to consider about the noise, we consider about the design time or time to market, we consider testability, we consider reliability, and usually the EDA problem will be formulated as a multi-objective optimization problem. And due to the very significant increasing in the number of transistors in a single IC, the entire scale for IC design goes exponentially. So it makes the traditional like heuristic-based EDA algorithm face some scalability problem and even also some reliability problem due to the advanced technology. They have a lot of new design rules you have to consider about that. And for the entire EDA, as we know, usually the main idea is that we consider that we will have a very large search space, and we will try to get the best one from this large search space with a very low latency. And the good news is that for the machine learning part, the machine learning actually can generate high quality solution for a lot of NP complete problem. And as you know, the EDA usually have a lot of NP complete problems there. So that means that we can easily extract the high level features or patterns from the design. And based on this important information, we can avoid to repeated complicated analysis and use this high level abstraction to extract the meaningful information we want. So it leads to a very impressive improvement compared with traditional methods when we apply machine learning to EDA. And this actually slides is catched from the ICCAT 2024. ICCAT is the best conference in the EDA field. And for that conference, we invited Dr. Brandon Wang, the VP of Synopsys. And actually, at that time, he shows that actually the impact of AI almost goes to any kind of design metric categories nowadays. And he also shared short stories like probably 10 years ago when he had a meeting with all the head of BUs, all the products, and he just asked, how many of you are using AI for your tool? Probably only one and two people raised their hand. But for 2024, the same question leads to almost everybody raise their hand. Besides only one very senior guy and raise his hand slowly say, I'm the one who does not using AI now, but I'm trying to put it on my tool. So as you see now, actually, not only the big EDA vendors like Synopsys, Cadence, they consider to put EDA into put AI into EDA, but they also consider about put AI into the entire system design to speed up the algorithm and hardware software co-design, consider about the multi-physics. So nowadays we claim that for the EDA, system design, and AI and machine learning, they will be like the whole family. You need to consider about that. And in more specifically, now we have two important research directions. One we call EDA for AI, and the other one we call AI for EDA. So for my research, we targeted on AI for EDA. That means that we use AI methods or machine learning models to help the traditional EDA problem. But for the other side is EDA for AI means that now if you want to do a very good training or inference, you must have like the NPU or TPU or some specialized hardware that can execute the corresponding AI program very efficient. So also we may need a lot of hardware that can help this kind of AI software execution. So how we can build this hardware very efficient, we also need the EDA tool that dedicated for the AI hardware. So that research category we called EDA for AI. But for today, due to time limitation, we'll only discuss the AI for EDA. And as you know, not only Synopsys but also Cadence, there are the two major companies for EDA tools. Now, if you directly use their tool, you will figure out they have all their tools integrated with AI. So Synopsys have Synopsys.ai, and they have a full stack AI-driven EDA solutions for the entire chip design from spec. Automatically RTL generation all the way down to automatically layout checking. And for the Cadence, they also have their platform called Jedi. And the Jet AI platform is a very smart one. They cover almost everything, like the verification, like the front end design, logic synthesis, and the back end design, physical design, so on and so forth. And for research in AI for EDA area, actually, in the very beginning, probably around the 2020, people will use very traditional machine learning method like SVM, like the random forest, like the tree search-based solutions, or for example, like the regression to find a solution. But recently, probably 5 years, we concentrate on more neural network-based solution. So usually we use a convolution neural network to have like the image-based data feature extraction, and we use the RNN to consider about spectrum data, like the text or audio, and we use a generative adversarial network, a neural network. Actually, they have two engines. One we called generator will give you some output, and we'll also have the criticizer to identify whether the quality of generator is good enough or not, or it's still need to be improved. So these are also very useful in the EDA. And for more recently, you also consider about the deep learning part, and we consider about the graph neural network. Since the circuit, if you consider about the gate level analysis, this is very suitable to represent your circuit as a graph with node and edges. So GNN will be very useful. And also in most recently research, people working on transformer, working on large language model, and we would like to have some research is like, if possible, we can directly get the spec, and then we directly generate the corresponding Verilog instead of use engineer to write the Verilog layer. So this is things we call the Verilog generation. And also the other type of the research is working on how we can set the parameters of the CAD tool very efficient. So usually, as you know, if you use commercial EDA tools, there are so many parameters you can do the setting. And usually it depends on a very experienced senior engineer to get the correct or very the most suitable values there. But actually, now a lot of people working on we can use large language model to generate the corresponding parameter to help you quickly find the very good parameter setting so you can increase the entire conversion speed. And of course, if you use AI for something, there are a lot of challenges. And for AI for EDA, at least the major challenges here. But I have to emphasize a couple of things. The first one is about data availability. So when we do this kind of research, the most difficult way is that how we can get sufficient training data. Since each IC design company or even an EDA vendor, they protect their data very, very well. Not like the AI or machine learning community. They encourage people to do open source, but you are not allowed to open your design or even open your technology file. So with this kind of limited labeled data and imbalanced data, how we can handle this kind of situation? This is the first the big issue. And the second big issue actually comes from integration with traditional EDA tool. Because now, since some people are building like the full stack automatic or say AI-based flow for EDA tool, but actually more practical ways that you still use traditional EDA tools like Cadence or Synopsys something, but for some specific point, you can use the AI to optimize it. So it's very important that you need to consider about the tool chain capability and how you can do the adaptation. It means that for the EDA tool chain to specific step or stage, you can export something out and get into your AI engine to do optimization and feedback it back to the entire EDA tool flow to continue their work. So this is also the main challenges we face it right now. And of course, the other important thing is generalization problem because the different kind of applications will have different design spec or different design characteristic. So it's very hard that you can find one generative model that can suitable for all different kind of design. So in this kind of perspective, sometimes we need to train a model design by design, but this is not very efficient. So how to make it like more generalized with a domain specific training, and you can directly adapt into the new technology or the major challenges we are facing on. And for my group, we are trying to solve this problem by actually to have some collaborations with real companies, and we try to put our machine learning related EDA tools into the company EDA flow so that they can smoothly combine with a traditional flow with commercial tools like cadence or synopsis. But with our portion, actually, we can try to escalate or we can get the better the solutions or qualities to do a better optimization. All right, so this is like big picture. And this page just give you the idea that this is not only us, but there are so many researchers working on AI for EDA. So these are some previous works from survey paper. And by the way, this survey paper just published in 2021. Oh, they have so many papers, but for now it's like even double or even triple. And usually when we try to do the machine learning and heuristic is like, since the machine learning probably cannot get like 100% accurate solution, so you probably can use machine learning to get to find a very good starting points and then use traditional, for example, simulated annealing or generic algorithm-based design space explorer to get a more concrete or more accurate results. Or you can use machine learning to do some prediction. And based on this prediction, your original refinement algorithms can find a better way to do the optimization. So these are the two things in our group we are developing right now. All right. So as you see for the different kind of stage, actually for the placement part is like a most limited situation in the 2021. So actually we're starting from placement, and we have actually have our 2D and the 3D reinforcement learning based placer. But due to time limitation, I probably have no time to talk about that. But I'm going to share the other framework we have done is called design rule check violation prediction with machine learning. All right, so what is this? As you know that DRC is a very important process to verify where your layout or your design satisfy a specific design rule under certain technology. And the design rule setability is very important since they define, for example, the distance between two modules or the minimum width of a poly or a wire or something. Violating this kind of design rule may lead to difficulty on manufacturing or even give you malfunction tap out chips. So it is important that you have to clean all the design rule problem before you do the tap out. And as you can see, just this figure just showing you that, for example, if you violate the minimum distance between two metals, they may have some spacing violation, they may show together. And for the specific wire, if you avoid violating the width problem, it also may cause a short situation. So actually, it is very, very important to follow. But how or when you can do this kind of design rule check violation? Usually, we have to wait until the entire design procedure finish. So that means that you need to do the floor plan, placement, global route, detail route, and you have your GDS2 layout. And with this GDS2 layout, you go through the design rule violation, and you can have your DRV report. And of course, the story is that once your DRV report showing that there are too many design violations. You need to fix them, right? So for the easy part is like missing the distance part or something. Actually, you can just go back to detail route or even go back to global route to do the finishing, to do the fixing, and you can finish it soon. However, if there are so many very serious DRV, for example, two cell overlapping, then this is not the case. You can just solve it from the routing, right? You need to go back to the placement, or even you need to go back to the floor plan to redo it and re-go through the entire design procedure. However, we use one industrial benchmark showing that if we have like 1.9 million instances and also have 2.25 million of nets, then if you want to go through the global route, it will give you average like 2 hours and maximum 4 hours. It's still affordable. But if you consider about detailed routes, actually average is more than 1 day, and maximum it will goes to 3 to 4 days. So that means that you spend 2 to 3 days to go through the global route, go through the detail route, and finally you get the results. Okay, these have very serious design rule violation. This is not able to use. You need to go back and then to have the other 2 3 days or even 3 4 days. So this is very time consuming and very non-efficient. So we have a key idea is that why not we leverage the machine learning model and we can develop a fast and a precise predictor that can estimate potential design rule violation at early stage. So that means that how about we just have a finish our placement, we can do the estimation, or finish the global routing, we have an estimation. So we can avoid that 3 4 days detail routing time. If the prediction model showing that this kind of placement or this kind of global route will give you a very serious design rule violation situation, we just give the update. We just redo the placement or redo the global route to avoid the time-consuming procedure. So the key objective is to utilize the machine learning framework to predict DRV locations at earlier means the placement and global route design stage. So this is the key idea of our research. And actually, this is also not a new idea. As you can see, if you do the placement and predict the design rule violation, there are actually the first work from 2015. But at that time, they used heuristic instead of machine learning and until all the way. And also, some people use global route to predict the design rule violation. And also, some people just use placement to predict the global route situation. However, we have one observation that these previous work only rely on a very simple machine learning model because they are the early time work, so they just use SVM or something to do the classification, and they only use either placement or global route feature. They don't consider them together. But we demonstrate that consider them together actually will give you better prediction results. And also, the most serious problem is they suffer from imbalanced training data set because when you get the training data set, actually we usually comes from the real design. But for the real design, the no DRV sample will be much larger than DRV sample. So this is important that you have to deal with this kind of imbalance in training sample layer. All right, so the main contribution of this work comes from actually we built a resonant-like CM model to predict the DRV. And then the prediction method is like we partition the entire design plan to the grid, and we want to predict whether each grid has a DRV happens to there or there's no DRV there. So this is the main idea. And we have 3 versions. The first one is we just consider about the placement information. The second one is we consider about the global route information. And the third one is we mix them together. And we also dealing with that now imbalance sample problem. So we propose another sampling technique to do that. And finally, actually, our F1 score can do up to 0.85. Of course, this is not very high, not 0.9 or something, but for the design rule violation prediction, this is good enough for the company. And actually, our work is collaborated with the Taiwan IC design company, and they already adapted this kind of flow into their EDF flow chain. And also the key is that we only need 3% of detail raw. It means that original 3 days now becomes like a few hours. All right, so now let me give you some details about how we can apply the machine learning to design rule violation prediction problem. So the key idea is that we have to introduce how we can train our model and how we can do the inference. And the second one is how we extract our feature. So we explain these two things. So let's take from the version 1 means that we just consider about placement information. So actually we divided our feature into two categories. The first one we call the grid-based placement feature. It is like the global information give you like the overall picture. And also we have the other things we call the layout image feature. In a specific target grid means a local feature. And I will explain why we need these two different type of features later on. And for our training flow, it's quite straightforward, just like most of the machine learning related work. It's like you are given a placement resource, and then you extract the global features and the local features by different extractor. And then you go through the detail route, and after the detail route, you should have the ground truth to show where the DRV happens and where the design rule is not violated. So you can have a violation indicator. And then we generate a corresponding labeled training data and also labeled validation data. And then for the training data, we go through the undersampling first and then train our CNN model and use validation data set to validate our performance. And if the model, CNN model is strong enough, when we do the inference, it's the same thing. It's like we give a placement, we extract the global and the local features, set into the CNN model, and we give you the corresponding design rule violation prediction. So the flow is quite simple. But the difficulty is that how we represent our feature, how we represent our circuit. So we follow the most of the PNR previous work is like we use grid-based feature extraction. The idea is that we divide the entire design into fixed sized grid, and each grid size 4.5 multiply 4.5 million square. So it's like this way. And we, for each grid, we extract their features and the label. So the idea is that when for this grid, if they have the DRV happen on it, we label this as a 1, means that it is a design rule violation. And for the grid, they have no design rule violation, we label it as 0. And as we mentioned, we have two different type of the features, right? The first one we call the global feature, also we call the grid-based placement feature. It is that since the design rule violation usually not directly happen to one grid, it probably happen to multiple grid because you can consider if there are two wires that are too close, they suffer from DRV. So it means that if the grid only cover one wire, the other wire actually also influence this wire. So it means that you need to observe the global information. So what we do is we create things we call the observation window, where the central of the observation window is the target grid, where we are going to predict this grid has DRV or not. And we following that we also take the adjacent grids to be the observation window, and we put the features of the entire observation window into our model. And for the other one, we call the layout image feature. So for layout image feature is like fine grain, it's local information. So we only consider about the layout image feature to the corresponding grid or target grid we would like to predict. And then we send these two different type of features to the model. And finally, the model will give us whether this grid has DRV, means that it give you the prediction result 1, or this is DRV free, give you the prediction result 0. So the idea is that. Then the next story is that how we can extract the features from each of the grid. So here, for the global information or grid-based placement features, the main idea is that we have a 23 by 23 as observation window, and for each of the grid in observation window, we extract 5 different type of placement features there. And total leaves 121 features in each grid. And their corresponding feature are floor plan attributes, instant attributes, net attributes, placement blockage attributes, and the routing blockage attributes. I probably have no time to explain all the detail about each features, but I will give you a big picture about what are they. So for the floor plan attributes, it's like we give you a big idea about the entire floor plan. So we consider about the design boundary, what is the row area, what is the site count, and for the corresponding routing track, we consider the check number, routing the capacity, so on and so forth, lead to 39 features. And for the instance attributes, probably use this figure to explain. The instance attribute is actually consider about what actually the instance is inside the floor plan. So we consider about the standard cell area and the number. We consider macro. We consider sequential cell number. We can consider fixed instance. We consider instance complexity, so on and so forth. And then we consider about the net related attribute because DRV actually has very strong relation to the net. However, we are in the placement stage. We don't have global route or even have a detailed route information. So the only thing we can consider about net is the bounding box. So that means that we give the corresponding pin location here and we have the corresponding bounding box. And based on this bounding box, we can see for each grid how many pins there, what is the net area, means the portion of the bounding box to the entire grid, and how many nets go through that, and where this net is inside a grid or outside of the grid. So we have this kind of features there. And also we have some placement blockage and the routing blockage, where these blockage are usually to be placed because you may have some macros or you may have some special net, means the power ground net or clock net you need to go through. So you block them to go to have the cell state layer or you have a signal wire go through layer. So totally actually we have a 5 placement blockage and 54 routing blockage. By the way, for this 54 routing blockage is total, actually we will have 6 features in each layer, and we assume the entire design have total 9 layers. So each metal layer will have separate features. So we totally extract 54 features. All right, so this is a global information. And the next story is that why we also need the grid-based placement feature, why we need the local information here. Here we'll just give you an example. As you can see here, we have for example, if this is one grid, and for this grid, we have 4 standard cell in there, and one is placed like left-hand side, the other one is placed like right-hand side. So as you can see, for the 4 cells placed at the left-hand side, the corresponding cell number is 4, right? But since they are not put it very closely, so when you consider about the pin accessibility problem, means that this is the most bottom level, and for each transistor, you probably need to have a connection to the other transistor. You have a pin to go through up to the other metal layer, right? So in this case, actually, since they are far away, so you probably may not have a pin violation problem. But for this situation, because they place very close, so they may have a very high pin accessibility problem. If you go out pin from this one, also go out pin from this one, they may violate the design rule they may violate the design rule because they are too close. But if we consider about the global information, we all consider these two situations as cell number 4, cell number 4. So of course this is not make sense. So we argue that we need to have a more detailed information, means the layout image, to tell the difference between this situation and this situation. So what we do is that for the target grid, we use a pixel-sized feature extraction, means that we consider each of the pixel. And since we just consider about a targeting pin problem, so we consider about connected pin on M1, M2, clock pin on M1, M2, and power and the ground nets, and also other intra-cell nets on M1 and M2, or macro or outer boundary. So we generate a corresponding 8 channels for that. And for each of the pixel, we get a value depends on the overlap between the things we want to consider to the entire area of the grid. So finally, we have this kind of 8-channel based layout image feature. Okay, so now we have two different kind of features. Global one, they have hundreds of features, give you like overall picture, and it's sent into the model with the observation window 23 by 23. And for the layout image, it's only the target grid, and it's like pixel based information. All right, so finally, we have all the feature prepared. The next story is how we can do the undersampling when we do the training. So the main idea is that, as you can see, if we divided the sample into 3 categories, what we call the DRV located means the DRV happens here. And the second one we call the DRV surrounded means the grid is not affected by the design rule violation, but they have one grid have design rule violation nearby. So it means that is a high risk they may have DRV. And also we have a black one we call DRV away. So as you can see, actually the number of samples without the sampling, the DRV away have like the even 10 times or 60 times compared to the other sample. So it will dominate the result, it will dominate the model. So what we do is we randomly delete 90% of the DRV away grids to do the downsampling, but we will not make it as 1-to-1. We can make it as 1-to-6, so that you will have still have the corresponding portion, but it will not dominate the entire the solution. So after that, finally we construct our entire senior model. So we have a observation window here, and for the entire 23 by 23, we have a CM based network. And also for the layout image, we have the other network, and we concat it together, and finally, we can predict whether this grid has DRV or not. And this page shows the detail of the machine learning model. Actually, it's like a ResNet model for the layout image one because the image, so we have a residual block. And for the placement part, actually, it's like more simple. We just have a convolution, average pooling, and flatten. And the concatenate is nothing but just a fully connected network. So this is a very simple version. All right, so finally quickly show you the corresponding experimental results. We have the CPU, GPU, and we use Cadence Innovas to be our ground truths. And here are some Python version and the TensorFlow and some parameter settings here, and I go through all the details there. And we use 11 industrial benchmark, and they are all in the 28 nanometer technology here. From D1 to D11, have different number of macros, instance, nets, and the grids. So give you the different idea. They have some of them is very large, and some of them is relatively small. And for each design, we generate two different floor plan results. The one floor plan based on one floor plan, we may have a lot of different placement resource. That is for training. And we have the other one, distinct floor plan for testing. So the testing set is separate from the floor plan one. And we also use confusion matrix to show the corresponding result, and we use F1 score to evaluate our final results there. And here, actually, I have to emphasize something. Of course, the true positive and the true negative is good. Is what it means we predict very well. But consider a situation for the false negative. It means that actually you have DRV, but you miss to take it. Of course, this is something very terrible, right? You take it very happy, but actually they have a lot of problems. So once you go through all the entire design flow, you freak out. This is not the case. You need to go back and to do it again. So this is the thing we need to take care about that. But how about the false positive? False positive means that actually there's no DRV, but you predict it as there's a DRV. So at the very beginning, we think false positive is not very serious because you just have found false alarm, right? But when we discuss with the company people tell us false positive is also very, very important. Because if you have too high false positive, actually the experienced designer will think this is not acceptable placement result. You need to do the replacement again. But actually, this result is good enough to continue. And if you do the replacement, this is also a huge effort. So it will also impact the time to market. So company will also take care about the false positive. So this is very different from our intuitive. Then, as you can see, the final results, as we can see, we actually have a very good number of true positive and true negative. And for the false positive and false negative, actually we make it as balanced situation. And our F1 score can reach to the 0.79. And we also check about the what actually is the importance of these kind of two features, the global features and the local features. So we do ablation study. We try to use one feature to see whether it can give a accurate predict results or not. So finally, you will see if we consider about the global information, this is still be okay. This or the F1 score is 0.77. But you only consider about the local information. You just have a pixel information. This is completely not okay. Yeah, but if you put two things together, actually you can have higher F1 score. So they give you the idea that if you want to have a more accurate results, you should consider about the local information. But of course, you consider about the local information, it will take extra like training time, of course. And also if we consider both of them, you have even longer time. However, if you consider about like the average detail routing time, the portion is like only like less than 3%. So we think this still be affordable. So this is like a first part. And by the way, just quickly showing the resource. This is the actual design rule violation. This is our proposed CM-based prediction. This is our prediction. Obviously, you will see the other previous work use FCN is completely missing a lot of things. But our results is very similar to the ground truth. And also in this case, it's the same. We can clearly tell the situation here, but not the previous work. And also this case, previous work can almost predict nothing. All right, so this is the first version. And the second version, since first version we got 0.7 something F1 score, we want to improve it. So the main idea is that how about we also consider about the global route information. Since global route is more near to the design rule violation in the entire design flow procedure. So how about we just try to use global route information to predict that? And in this case, actually, it's very simple situation. So we have 6 value of each G cell to consider it as corresponding features. We extract only 6 features, and then we still use the 23 by 23 observation window, and the entire problem formulation is the same. We try to target to try to see where the target grid has a violation or not. And also we build a very simple CM-based network here. Also, you will see it's only convolution, average pooling, flatten, fully connected, and softmax, and that's all. And finally, very interestingly, for the global route situation, actually we get a F1 score is 0.79. But for the placement, actually same 0.7949, and this is 1.2. Of course, you will see placement give you even richer information because usually people will think about global route is more near to design rule violation, so it should be given like the better prediction result, but not the case here. So this is something we freak out. This is a very interesting thing. And compared to some previous like global route congestion map prediction results, again, our proposed CN can have a better results here. So finally, we have the other idea is that okay, so global route actually give you not very good at, but I should say a little bit worse than our placement version, but still be good enough. And for the placement, they have a very good results. So next question is how about we consider both of them together? Right. So this time we consider both placement and global information together. And we have the same thing. We extract the total 124 placement features. The only one difference is that since now for the global route, the commercial tool have the GCL, means that we are not using the uniform grid size. We use GCL as our the target prediction target. So we also need to get a GCL size as our feature. So we have a grid height, grid width, and grid area as our extra feature. And for the other features are the same with the previous two works. And finally, we have the other a little bit more complicated CM model architecture, but still be very simple. And finally, with regards, we got a very significant improvement for the F1 score. But we also need a little bit extra runtime here. So let's give you the conclusion that actually, if you have better or say even more rich features like global route information added in with a little bit extra timing, you will have significant improvement on your prediction result. So this version is what company feel very happy. So finally, the company get this version and integrate it into their entire EDA flow. All right, so quick summary here. For this work, actually, we do the design rule violation prediction framework, and we have a placement information, we have a global route information, and we combine them together. And we also trade off between the prediction accuracy and the runtime efficiency with these three different versions. And also, we apply undersampling to all of the versions there. And we figure out that we can have a very high F1 score, but we only have like only 3% compared to the detail raw. Means that 3 days you just have like 3 hours or even 1 hour. So it will give you a very significant runtime improvement for the real EDA flow. All right, so this is the first part of my talk. And I know that's almost run out of time since I have only 10 minutes left. So the next part, I will just give a very high abstraction level of how we also can apply a very simple gradient descent-based methodology to consider about a pin assignment problem, especially for fifth rule pin. So the idea is that pin assignment actually is also a key step in physical design because if you put a pin at a different location, actually it will give you different start and ending points of your routing. And of course, it will influence your total routing violence or even your congestion situation. And through a different kind of pins, there are very special pins we call, or sorry, we have a very special pins we call the feed-through pin. So what's a feed-through pin? Consider if you have a SOC like this way, and you may have some signals you need to communicate between block B and block D, and say if there are very limited space for the corresponding channel at the top level. So when we need to do this kind of communication, we may need to get into the design C and get it out, but we will not touch all the design in the design C. These things we call the feed-through net. And for the pin of this feed-through net, actually we call feed-through pin. So this is a feed-through pin, and this is the blue, the green one is the feed-through net. So we have a observation that if your fifth through pin assignment did not do a very good location like this situation, then your corresponding routing inside the block C may go through a very congestion situation where the yellow one means there's a congestion region. So actually it will lead to this block internal routing being very congested, or you may degrade its performance or even lead to non-routable situation. However, if you have a appropriate pin assignment location, actually you can have a better resource layer. So our problem is that, okay, given corresponding placement resource and also given the detailed routing information about the wires in the block, how we can do the fifth looping assignment so that this fifth looping will avoid the congestion area but also still match the timing result. So this is what we do. And also we have the other observation showing that by removing only traditional I/O pins, their corresponding the congestion is not decreased. But if we remove only feed-through pins, actually you can see there are significant decrease on the congestion. So they give you an idea that feed-through pin will cause the congestion. So if you do a very good assignment for feed-through pin, you can avoid the congestion. So this will work. Actually, we propose a framework we call the COPA, and this is like the first study to consider congestion-oriented fit-through pin assignment. And we propose things we call FCAM, means fit-through congestion avoidance matrix. And we use a gradient-based method to guide the pin movement. And finally, actually, we can reduce the total overflow by 7.6% in the average. And also, we can have 3% to 4% lower total overflow compared to the commercial EDA tool right now. So, by the way, we have some assumption is like we assume that the placement and the clock tree synthesis are done, uh, and we assume that the given placement are fixed placement. You're not allowed to adjust placement, and all the fit-through pin are 2-pin nets, and we have a pin alignment constraint, boundary restraint constraint there. And this is like the formal problem formulation. I'm not going to go through the details due to time limitation, and just showing you the entire framework. So the idea is that after you get a place a block, you do the data extraction. So you have a placement information, the fit-through analysis information, and what we do is we do a congestion estimation by our FCAN calculation, and then we use a gradient calculation to guide the pin to move to the appropriate location, and then we see where the converge exceed a maximum iteration. If not, we continue to do that until all the fit-through pin location are decided. So here are some mathematical formulation. I'm going to skip it out. But the key idea is that we define the FCAM, where they have some idea is that we consider about the bounding box of the corresponding net and how congested the corresponding grid had. So we have like the prioritized or weighted equation here. And the next story is that we model this kind of equation to be a bell-shaped situation since we want to do the gradient descent, and we should make it differentiable. And by doing the differentiable, we can guide the pin to move to the appropriate direction. And at last stage is that since the pin actually is not for the pin location, it's not a continuous solution, it's discrete solution. So we also need to consider about a pin alignment problem. So we have the other mathematical formulation to satisfy that alignment situation. So finally, just quickly show you the corresponding experimental resource. I just showing this the final resource here. So this is the pin assignment provided by commercial tool, and this is our resource. And we compare two things: the total overflow. The total flow means that the routing confusion situation. So the number should be as small as possible. And for violence, of course, we also need to make it as small as possible. So you can see that compared to the previous resource, our COPA framework can have like averagely 7.6 improvement on total overflow, but we only have very slight wire length increasing, which means that our resource is very competitive to the real design. And we also consider about simulated alien based version. Of course, our version is better. And we compare to the commercial tool Innovus, and we figure out that actually Innovus have not only a higher the total overflow, but also have a higher total wire length. So that means our resource has a very competitive situation. So this is also collaborate with a company, and companies now try to adapting this approach to their real project. All right, so this is like the entire picture. So I think I only have 3 minutes left. So finally, quickly showing you. In my group, I still have some research related to AI for physical design, like the PDN optimization and agent mitigation procedure. And also we consider about 2D macro placement. We have a heuristic-based version, and we also have a reinforcement based version. Now it's under review of AICAS 2025. And also all these research results give me some awards, also for some best paper awards in the 2025. So I think it's almost the time here. So I'm going to stop, and I'm happy to taking questions. Thank you very much, and sorry for a little bit rush. Yeah.
And thank you very much. We have 2 minutes for questions. Do we have any question? Uh, uh, am I correct? Is this these methods presented here, and is this the kind of outcome of the projects in the ACDRC or not?
Partially yes,
Yes.
partially not. Because for the
Okay.
ACDRC project, we are now working on applying this method to the anode circuit design. So actually for ACDRC project, we consider about the symmetric or some resistance effects or something, and we try to develop our placer and our router to do that. And during this kind of development, for example, like pin assignment idea, we can
Uh-huh.
apply to ACDRC project. But for honestly, for the DRC violation prediction part, is still be a little bit far since that is a digital based design. And I'm also thinking about how we can move it to the anode circuit design. And also for our ACDRC project, I'm currently working on to submit the AE conference with our partners right now. So I'm not sure in it's because we are still preparing for the paper submission. Yeah, but if the paper got accepted, I'm very happy to come back and share the ACDRC project outcome, especially for using AI to do analog circuit placement, analog circuit routing, and also the analog circuit resistance placement the problem. So this is the actual things we are working on right now.
Okay, okay, thanks. It seems to be quite promising method for this case.
Thank you very much. And by the way, here are my email. If you have further questions you want to ask, you can just send me the email anytime. And I'm very happy to have further discussion with all you guys, or you can have some ideas here.
I cannot see
Yeah.
děkuji in Czech
Yeah.
language.
Which one? Dikui. Nice, nice, nice.
Okay, and thank you very much once again, and hope we will meet in person in quite close future. We will
Sure,
have some.
sure, sure, sure. Yeah, after my family issue has been solved, I'm very happy to travel again to Brno and to meet you in person. And also, you are always welcome to come to Taiwan and visit us. Thank you so much.
Yeah, we will plan it on September. Semicon and this stuff.
Oh, good, good, good. September. Okay, great, great, great.
Okay, we will manage that. So thanks a lot. Thank you once again.
All right, thank you very much. Thank you very much.
Okay, so let's proceed in the program, and I guess now the floor will be given to our colleagues from CTU Prague, I suppose. Roadmaps, okay?
So let me introduce first to save time. My name is Jan Schmidt, and I'm here on behalf of my respected colleagues from Safety Lab, from the Department of Digital Design. Nowadays, when it comes to the safety of an autonomous car or other device, everyone cries challenge, challenge, and challenge. But few people realize what the reason or what the cause reason thanks are. So I will try to start with the very simple beginning and give you some analysis with the vision of getting some framework for safety evaluation of autonomous devices. I'll show you some promising ways ahead. I have met, and finally, I'll talk about the intersection of safety and security. So, well, I've got no driving license, so presume that CTU provide me some autonomous device, some autonomous car one day. So I'll come to it. Do I trust it? May I enter? Possibly, yes. I've got some experience with that, and it ran fine. And first of all, it's street legal. That means there is some certification authority somewhere, an office. Everyone hates them, and everyone trusts them. So that's a public proxy for trust into autonomous into safe device. Of course, they cannot certify each one car, so they certify its design. So I trust the design. Now there's more to it because I've got to trust. Want to trust to the manufacturer for manufacturing it correctly, people for maintaining it correctly, and so on. And this is already a trust in a process, which is not every time distinguished. So I'll shift my focus from trust in a concrete device to a trust in a device. So the usual question is the device safe in the case of a fault? This is the classical approach to safety. So we've got something from practice. We can test the design, which is artificial practice, and we can simulate. Okay, I've heard already here that no one trusts simulation, but still it's an imitated practice. So, in fact, trusting in a design means trusting in the results of verification and validation. Then another question is, and sometimes it has got the separate standards. The device, whether the device does what is intended, so whether it conforms specifications. So, well, before software came into such devices, it was easy. Now, we have to trust in the software development process. We've got to trust the deployment process of the devices throughout development, production, operations, and so on. Now, assuming the device does what it should do, what it was intended to do, there is another question: is the intended behavior good, safe, tolerable, and so on? And you can see here that it's got even a different standard. So the safety of the intended functionality is a new concept. The UL 4600 seems to integrate both. So this concept is based on operational design domains. So, well, the car can say, well, the road is too slippery. I don't accept that. use your feet. Or so if it detects leaving the operational design domains, which is dry, straight roads only, etc. So it reacts. So we have to analyze various scenarios. We've got methods for validation, etc. So this is a trust in the specification process, specifications as opposed to design. But in the case of autonomous devices, there is the challenge of the open environment. The reality, the street life, the traffic around and etc. is unpredictable, ever changing. Something new happens already. I will show you some later some cases. So any description, any specification of the external environment is inherently incomplete and insufficient. So we cannot have a full test coverage for a design, full simulation coverage, and so on. And we can even have no full test coverage for specifications, because yes, we have many methods to analyze specifications. We can analyze risks. We can analyze the possible scenarios. We can develop some safety metrics and other approaches. But there always can be a surprise in reality. Well, these are traditional established techniques when we have a specification by description, and recently we can even have formal specifications. We can reason about completeness and non-contradiction and so on as to be published, but yes, we can check them manually, simulate, and so on. Starting with such specification, we can trust the process through whether the requirements of the specification can be traced through the design process up to the design. Code reviews, quality assurance, testing, and so on, or even having something that simply turns the specification automatically to the design, so-called design for correctness. But even such software can have bugs, as we know. So that's the say standard situation. But now with machine learning things, the specification is not by description but by examples, and the question is, of course, are the examples any good? Are they sufficient? What's their coverage? And then so on. So specifications are quite questionable. Then the process can be trusted to some extent. We know how to train the machine learning networks and so on, sort agenda properly and so on, but we cannot trace the requirements of the specifications through the process. So the question is, how do I build trust in such a situation? Well, the way ahead lies in the fact that safety is always about probability. if probability is, I don't know, 10 to the minus 16th per hour, we can say, okay, that will never happen in my lifetime, and then that's it. So everything starts to be probabilistic. We can prove first of all, we can tell the sufficiency of the specifications in a stochastic probabilistic way. We can measure the training quality in a probabilistic way. The minus or the cons is that when we start using probabilistic methods somewhere in the safety reasoning, we'll be forced to keep it everywhere. But still, a way ahead does exist. So what I'm talking about is, and what's the interface between the designer, constructors team, and the certification authority is the so-called safety case, which is formally specified in several standards. But basically, it's a structure argument, complex structure argument, which must convince the authority that it's okay and it's safe for use. Now, this cannot be monolithic, as still we cannot design a monolithic AI piece of AI, some transformer to control the entire car. We cannot write a safety case about such a black box, except as one author of the UL 4600 put it, except you ride 100 million miles, and then you can be reasonably sure that it's safe. So the key word is that the argument is structure. So it's basically a building, possibly irregular, possibly differing with each case, possibly of some very complicated shape. When dealing with safety, with descriptions of safety, any design, in fact, is at least two hierarchies. Either its global function is decomposed to some smaller functions, etc., till some primitive functions done by something, or it's a component hierarchy. These are two approaches, and then some methodologies, some safety methodologies differ in which hierarchy they use. So yes, it's hierarchical, it's complex. Now, our problem is that given smaller safety cases for the lower levels of hierarchy, we have to construct a trustworthy, of course, safety case for the whole. And that would be the task of some frameworks. So to recapitulate, what does that mean for a framework? It's hierarchical, it's functional, or structural, or both. In which case there are many complications. It has to reason about design, processes, and specifications because it builds the trust in design processes and the specifications. And because the building stones, either the functions or the components are so different, it has to use logic, reasoning, proofs, etc., hard logic, or stochastic, probabilistic methods. So, when we go along the path of functional decomposition, usually we've got some sensors which put data into perception or pre-processing and so on. Then there is a step called sensor fusion, which from the perception of the sensors builds up situational awareness for the control. The control then plans actions and puts it to the actuators. If those functions are able to report their health, their function, it's a great help for the design process and for the safety case. However, we all know that transformers cannot see, I don't know. Instead, they shamelessly hallucinate anything from technical data to historical facts. So the class of the data on health actually is missing. As a way ahead, and an interesting approach, I'll give you a simple example from the railway domain. The task was for an autonomous and slower freight train to see an obstacle on the rails. So there were cameras, perceptions, and they put it something that is, in my opinion, something between sensor fusion and redundancy, so on. And the reason is obstacle, no obstacle, free rail. And the requirement was that false negative intensity, so that saying no obstacle and then running into it must be less than 10 to minus 7 per hour, given the frequency of stones on tracks and so on. So the first step taken by the authors, Char here, was to put their parallel perception channels and parallel sensors, one heuristics, one machine learning. In that case, a CNN. Well, it's a railway world. The system integrity level is that the railway world is not the automotive system integrity level in kind of automotive world, but this requirement, which corresponds to system integrity level 3, is roughly in practice, because the measures are different. It corresponds to ACIL D, which is the most stringent. So, how to prove that the machine learning part was training? Well, they exclude traditional mistakes like overfitting and etc. By proper training and methods and so on. But and that's the contribution. They managed to prove that the training set is sort of kind of representative. It's based on measuring their similarity, or measuring their semantic equivalence, and putting a cluster analysis on that. So they were able to identify cluster equivalence clusters in the training set, and then using some very large image database. You see the gigabytes of the training sets are therefore small, right? So anything much larger. Randomly picking from that database and putting that to the equivalence classification system, they were able to prove with some given probability that the equivalence clusters cover the whole reality. Similarly, they were able to prove that the hypothesis that there is some unknown new equivalence cluster is false. So that's the principle, and the key trick in that is that they look at the training images not as discrete things, but as a points in a continuum. And then they are able to find paths between the two images. Well, warning, this is only an illustration. Right? So one image, my neural network says there is an obstacle. So a combination, or just in this case, a linear combination of two images, my network says it's an obstacle. Finally, this picture again, it's obstacle. So because there is this path, this image and this image belong to the same equivalence cluster. Of course, doing the transition this way is not a path, because at this point my neural network says it's there is no offset. So the entire system, still we talked about this part only. They had to prove that the channels are statistically independent, which isn't quite easy. Then each pair of heuristic and CNN processor were given a pessimistic voter. So if one of the channels say obstacle, the result is obstacle regardless of the other channel. And a Markov process or a model checking proved that the probability was 4%, too much for the intended system level integrity. So what to do? The classical thing to do is to put the triple modular redundancy triplex voter, and then finally they arrived at a probability which was okay for system level integrity 3. So that's the example. Allow me a few comments. First of all, the equivalence clusters are seem to me very valuable tool for insight into training sets and so on. However, we need some experience with them because just to verify that the equivalence defined that way is really a semantic equivalence. Then I'm not sure whether we still need a full-fledged model checking on Markov models. Our colleagues developed methods that can process even hierarchical models, even non-stationary models, and so on. So that's some future work. And then, yes, please, TMR efficiency. You can see that we moved the probability from 4% to 2%, but at the cost of 200% overhead. And not only in silicon, but in sensors as well. And then, well, the paper wasn't entirely academic, but still they put the problem of failures in hard and software, as they put those problems aside by stating that they would correspond to system integrity level 4, which is used in the railway world. So now I'll touch the area of tensor fusions and the intersections of security and safety. The existing standards say you will have a security plan, you will have a safety plan. Perhaps they could intersect. They certainly do intersect. This is an instant and transportable fog for everything optical, right? You can buy it in the nearest supermarket. So, and of course, some people can use it with malicious intents. So there are, of course, methods to overcome that. They either are based on statistics. This sensor usually tells the same as that sensor, so we trust them, etc. Or we should do some reasoning with knowing what the data mean. If 5 sensors out of 6 caught fog, and the 6th one, which the hooligans didn't know about, did not, what does that mean? Right? It's one of six and still worry. Well, if you read the standards, there are methods described, what to expect, what to mitigate, required mitigation, by the way. Well, if I look at it, such ingenuity, such creativity, such out-of-box thinking that in a comparison, the standards and safety is boring. Well, as an engineer, I'm forever bound to the boring side of the fence. So that's it. That's fine. Well, there are many attack vectors. Those which do have a cryptographic or networking solution, I'll leave to our cryptologists. Those do not will require some integration into at least at the sensor fusion level, perhaps in other algorithms as well. So what will we do? We will of course, pursue the equivalence clusters because they are very interesting. We will dig into the ways how to prove trust into various devices, certification, and so on. And let me once more repeat the conclusions for possible frameworks. They are heterogeneous, hierarchical. They build trust into specifications, designs, and processes, and therefore they need integration of AI techniques, safety, and security, regardless of what the standards say. Now it's either questions or continuation, Mr. Chairman.
I guess we can have a question if you, and then we can continue with the other colleague from the CPU, I suppose. Okay, so
If no questions, thank you very much.
Because there will be plenty of time during the lunchtime to ask.
Ještě mi to vypnul. Jo. To byla chyba.
Jak ty studenti dělají, něco zajímavé.
No právě. Bez nezvedených učitelů, to je prostě. Je to laser. Aha.
A šipkodová.
Jasně, laser. Okay. So, good morning. My name is Martin Novotný. I'm from the Embedded Security Lab in our university. And let me talk now about the cryptography. So, we all are surrounded by embedded systems. We have them everywhere in our pockets, in our bags. Some of us have it in our body. Here in this room, there are many embedded systems, and there are some requirements on these embedded systems. They must be, first of all, they must be cheap. They must consume just only a fraction of energy. They must be small, and so on and so on. The other requirement is that they must be safe, because if they are built in, for example, into some automotive device like the car, or into the medical equipment like the pacemaker, they must be safe and not to harm human lives. And for the same reason, they must be also secure, because the safety is the resistance against the obstacles given by the Mother Nature, while the security is the resistance against artificial attacks mounted by evil human beings. So for that, now I will focus on cryptographic part on the security. And the evil people can mount many different attacks on the devices. There are several classes of the attacks, like the classical attacks, implementation attacks, and the social engineering attacks. Regarding social engineering, you probably know it because you already got the fake email asking you for the PIN number and so on and so on. So you know it. But the system must be secure itself by using the strong ciphers, which is currently the case in most systems. We are using strong ciphers, so the classical attacks are not applicable anymore. It was possible earlier, for example, the data encryption standard, which was introduced in the 70s. It was vulnerable to brute force attack because it was using only
the key that was only 56 bits long, and it was able to it was possible to break it within a couple of days, so no problem. But currently we are using advanced encryption standard, which is using at least 128 bits. And to break such a system with contemporary resources, we would need billions and billions of years, some multiple ages of the universe. We would need to break it. But on the other hand, we can break it only in 5 minutes, let's say, using the implementation attack, which are very strong. And I will talk about them in this speech briefly. So the implementation attack doesn't directly implement the properties of the cipher, but its implementation. And there are two categories, the two main categories of implementation attacks, passive and active, and I will talk about them now. So the passive attacks, what is the core idea about the passive attacks? The passive attacks require the side channels of the device. For example, if the attacker is breaking the mechanical safe, they can use stethoscope and listen to the sound that is going from inside of the safe. So the clicking of the wheels inside the safe. And when they distinguish that there is some different sound on one combination of the key or on one cipher, then they can say, okay, this is the correct cipher on this position of the code. So in this way, they can break the even very strong code, which may have multiple digits, like I don't know, 10 or 20 digits. In a while, in a couple of minutes, they can break it. In case of the digital device, we are doing something similar. This in this case, sound was the side channel. In case of digital device, we are typically measuring the power consumption, the power trace, which is depicted here. So the power trace or the electromagnetic emanation. So we are using small antennas that we apply close to the chip, and we measure the electromagnetic emanation that goes from inside of the chip, or the execution time, temperature. Acoustic noise is also possible to measure because all the chips are noisy. So if you listen to the chip, if you apply a microphone or your ear to the chip, you will hear the sound of the chip. So it's also possible. But in the case with the most common is measuring either the power consumption, like this by the oscilloscope, or the electromagnetic emanation. And by measurement, we get the power trace. And as you can see, the power trace is not constant. The power consumption is not constant. It rises at each edge of the clock, especially on the rising edge of clock. There are higher power consumptions. And you can also see that the power consumption at the peaks is not identical, because the power consumption depends on the instruction. Some instructions consume more energy, some instructions consume less energy. And how can we utilize it now? We can apply against several different attacks. One of them is so-called horizontal attack. So if we, for example, on the oscilloscope, if we zoom out to see the whole encryption, and if we focus only on the envelope of the power trace, then we can see that there are some repeating patterns. For example, AES is a round-based cipher. The basic version, which is using 128 bits, has 10 rounds. And if you look at the whole encryption, you can easily distinguish this is the first round, second round, third round. It's clearly visible. If running, for example, the RSA algorithm, which is for example, for the data signature algorithm or elliptic curve algorithm, then in case, for example, of RSA, we are doing exponentiation. And if exponentiation, or many times is implemented, we're using the so-called square and multiply algorithm. And if we do it in a straightforward way without any countermeasures, then in every step of the calculation we are doing squaring, and if the bit of key of the exponent is equal to 1, then we also do multiplication, and if it is 0, then we don't do multiplication. So if we do it this very simple way, then the attacker can see simply here in the first step we did only squaring. Okay, so the bit of key is 0. In the next step we did square and also the multiplication because it is longer. We did two operations, so the bit is 1 and so on and so on. And just from one power trace we can easily see the whole key, the whole secret key, just because the attacker had the physical attacks to the device and they could measure the power consumption. So this is one possibility what we can do, and VTech will talk about the countermeasures against such type of attack. The other possibility is so-called vertical attack. In this case, we do not measure only one power trace, but we measure several power traces. And as you can see, if you compare the power traces, then you can see that, okay, they are very, very similar because in every step, the device, the processor is doing the same operation. But still, there are some small variations in the power consumption. And this is because the fact that the power consumption depends not only on the instruction, but also on the data, on the process data, which are processed inside. And the data that we are processing are based on the input data, so-called plain text, and also on the secret key. And from this, if we do enough measurements, like I don't know, 100 power traces or 1,000 power traces, in some cases 100 million power traces, if we have sufficient data, then we can, by using statistical methods, we can distinguish what was the key used. And this is so simple that we teach it to our students and they can do it. And by the measurement and the following follow-up analysis, we can break it just only in 5 minutes. So it's very, very, very simple. So the other class of attacks are so-called fault injection attacks. And in this case, we do not use oscilloscope. We just only force the token, the device into malfunction, and we observe what are the results, what are the data that go out from the device. And how can we force it into malfunction? It's very easy, for example, by clock glitching or overclocking or the voltage glitching. And it's also very powerful because, for example, there are some attacks that were introduced in 1990s. In 1999 was one of them, Belcore attack, which is attacking again RSA using Chinese remainder theorem. And one of my students tried to apply this attack in 2024. So it was in 25 years after introduction of this attack to the microcontroller that was developed by Microchip. And equipped, it is dedicated for cryptographic applications. It is equipped with RSA accelerator and AES accelerator and elliptic curve accelerator and so on and so on. And he applied this attack to the RSA accelerator and he was successful. So you can read the paper, and he really was able to break it. There is very simple countermeasure how to do it, but you have to do it in software. So, but there is no warning in application data, application note, neither in the data sheet that you have to do it in software. Okay, so in our lab we are playing with the side channel attacks, and because we know that the side channel analysis is very, very important because it's side channel attacks are very, very strong. We developed a tool that we call Trace Expert, and you can install it freely because it's open source. So please feel free to download it from the webpage traceexpert.org. There are links to download it. It has graphical design. It supports both the measurement with the oscilloscope or with the antenna, and also the analysis of the data and display of the results. So please feel free to use it. So, okay, do you have any questions to this? Okay, thank you. And now VTech, place is yours.
Hello, my name is Ditek Mašek, and I'm a PhD student in the Embedded Security Lab and CTU. And I will talk about the protections against the attacks that Martin presented. So first I will talk about protecting symmetric cryptography, asymmetric cryptography, and if the time will be good, I will talk about authenticated root process against fault injection. So side channel protections, what we need to do, as you saw, we used that data correlate with the power consumption and the power consumption correlate with the data, and we use that during the attack. So we need to decorrelate the behavior of the device, the power consumption, the electromagnetic emissions, the timing from the secret key. We can use hiding in time, so include some dummy operations, clock adjustment, etc., or hiding in amplitude, some differential logic, current compensation. So like we flatten out the power curve. And what I will talk about today is masking. So we basically randomize the data that are actually processed in the device during the computation. So we use some randomly generated value that is called mask. And we made it so the intermediate values are totally independent from the secret value that is processed by the cipher. We use the fact that ciphers typically operate over some finite fields or groups, and therefore we generate some random mask and we can add it to the secret value or the sensitive value, or we can use multiplicative masking. So we just use multiplication here. And as a result, instead of one secret share, we have two shares that are basically random for each computation difference. And sometimes we need to convert between the types of masking, between, for example, the additive and the multiplicative. And here we have to ensure that we do it without ever revealing the raw valuable X. This is really crucial because even if we use this masking technique, we can still use it wrong. This is the example. For example, we need to convert from additive to multiplicative masking. So by naive way, we just remove the additive mask, we add the multiplicative mask, and hey, here we have the raw value of X during the computation. And that's the point where the attacker can target, and basically our countermeasures are not effective. So we have to rewrite this equation so there is never the raw value of the intermediate value X present. And similarly with multiplicative to additive transition. So now I will talk about concrete example how to use this technique to mask AES computation. You might know AES, it's a standard symmetric cryptography. The round is constructed by 4 functions, and we have to mask each of them. So first function is add round key. So we have some state variable X. We have the secret key K, and so we use additive masking, generate some random mask M, and apply the add round key, the mask value, and the mask out stays the same. With the sub-bytes, it's a little bit more complicated, and this is the example where we need to actually convert from additive to multiplicative masking, because we have to compute multiplicative inverse of the state variable. And if we use additive masking, you can check that this equation does not hold. So we have to convert to multiplicative masking, do the inversion with the multiplicative mask, and then use the conversion back to additive masking. And then because this transformation A is just some matrix multiplication, this is addition of some offset, it's both linear, so we finally computed the output of sub-bytes operation like this. Then we have shift rows. Shift rows is just shuffling of the bytes inside the state matrix. It doesn't change the value of bytes, so we just shuffle both of the share matrices, and we have the output. And with mixed column, there's this some multiplication of the state matrix by some constant matrix. All the operations there are also linear. So we just apply the mixed column function both on both share matrices, and we have the output. So we successfully computed the full AAS round without ever touching the raw value of the state. And every time we compute it again, because we use different random masks, the computation will be different, and we cannot use some types of attacks that Martin presented. Second, I will talk about how to protect asymmetric cryptography, concretely ECDSA. So with ECDSA, the algorithm looks like this, and we have two critical operations there. The scalar multiplication on an elliptic curve with the signature nodes K, and the computation of the signature response S. We have the signature key D here. Yeah, so how to protect the scalar point multiplication? That's the most crucial part. As you saw, Martin showed the square and multiply example of the attack. So we have to use uniform formulas for addition and doubling on the elliptic curve. We have to use uniform multiplication algorithms, for example, Montgomery ladder, and we can add some randomizations to the points on the elliptic curve like this. And we also have to mask the secret nonce. We use the same techniques as we use with the AES. We can use, for example, additive masking. So we generate a random mask M from the field FQ, and we simply add it to the secret nonce, compute the scalar multiplication. We compute the scalar multiplication also with the mask itself. Then we subtract the result, and we have the result R, and without ever computing the scalar point multiplication, really with the secret nonce K, but with this mask value. Or another method, we can use group masking. So we add some random multiple of the order of their inner group to the K, and we compute it that way. Really crucial thing here, always use mask of the same size as the value that you want to mask. You can imagine that, for example, here, if you choose, for example, 32-bit mask M, but because the K is 256 bits, usually the most significant bits will stay the same. You will mask only the 32 least significant bits and not the rest. So you have to also use the full size. This is a really common mistake that people want to save some performance, and they use just small mask, but then you only max some part of the key that you can brute force. If you use just 32 bits, it's easy to brute force. And second part, we want to mask the operation of the signature response. The equation is right here, and for example, you can do it in many of ways, but we can still generate the random mask T and rewrite the computation in this way. So you ever touching the secret values by multiplying with the T, which is random, and then you do the rest, and from there you computing with the random values basically. Yeah. And now I will briefly talk about fault injection protection, and I will focus on secret boot process, which is really important in most devices, not only cryptographically security devices, but almost every devices. And with fault injection, the solutions are very similar as in case with safety, because we expect some fault to happen and we have to behave somehow based on it. Either finish it correctly, so tolerate the fault, or return some error and fail in a safe, or in this way, secure way. From the safety perspective, this differs that what does it mean to fail in secure way? And also, my colleague Schmidt talked that it's probabilistic. Safety is probabilistic. And if the fault doesn't happen like that often, we can say, oh, yeah, okay. With fault injection attacks, you can be sure that it will happen because the device will be attacked. So you have to behave in a slightly different way. And how can we do it? Use redundancy, invariant checks. So some property must hold throughout the computation. Sometimes we can recognize that the output is faulty, and so more. So with authenticated boot process, what we want to do is to ensure the integrity and authenticity of the application firmware that is being run on the device. So we usually use a digital signature, for example, the ACDRC that I showed before. And during the boot up process, we verify that the firmware is indeed genuine and not changed during some malfunction. And the adversary then tries to, for example, skip the verification or alter this verification in some way. So the device boot their malicious application, and they can do sort of things with it after that. So with the ACDRC algorithm, it's really crucial that you always check for faulty signatures. So for example, signature 00 will always pass the verification. It doesn't matter what the data is, doesn't matter what the public key is, it will always pass the verification. So you have to check that this signature is not a valid signature, never. For example, the Montgomery ladder algorithm for the scalar point multiplication has a really nice invariant built in it. So you can check it periodically if there is not some alternation in the process, and a lot of other things connected to the elliptical cryptography, like check for points at infinity that should not occur anytime, etc. And you can also protect the program flow itself. So I selected two things here. I call it call checks and checkpoints. Call checks tries to protect call of a function. So you want to check that the function was really called. For example, you have a function ACDRC verify in the program. You want to check that the function was really called. And also you can add some checkpoints. So you not only check that the function was called, but you throughout the computation check that the program entered every critical part, and presumably also in the correct order during the computation. And at the end, you say, yeah, okay, I get some result, but I see that this checkpoint value does not match what I expect. So the program somewhere took another path that was faulty, and I behaved based on that. So to conclude the talk, I have 3 points here. Defense in depth. There is no silver bullet that will ever save you. You have to combine the methods and check for the robustness of your solution. Balance security is always cost of area and performance. So you have to choose the right level of security for your threat model. And the security, hardware security is always infinite game. The attacker is always a step ahead of you. Attacks become more powerful every system is buggy. That's just a fact. So your protections must evolve, and you have to be prepared for being hacked. I don't say it will happen, but you have to be prepared for that. Thank you.
Okay, we are slightly delayed, but still we can ask one question if we do.
Maybe
And or
Yes, after
okay,
questions.
I have a question. I know that the standard is now to implement the algorithms like in the hardware. Yeah, that they are not run in the software because it's safer. I don't know if it's something you are focusing on or not, but can you tell me what are like the main differences, for example, or differences like the main issues trying to implement the algorithms, for example, the mask AES in the hardware?
Yeah, so the symmetric cryptography and also, for example, some hash functions are usually implemented in hardware because it's pretty simple to implement it in hardware. So it usually is. But for example, the asymmetric cryptography, so elliptic curves, RSA, or even now the emerging of post-quantum cryptography, so on some lattice-based. These schemes tend to be quite complicated to implement in hardware, and therefore we usually use some hardware-software co-design. So for example, with the elliptic curve cryptography, you implement just the building blocks, for example, the finite field arithmetics in the hardware, you optimize it for speed and security, and then you implement it in software, like the whole scheme, for example, the ACDRC.
Okay, thank you.
yes, thanks a lot. So that was the one, and
I would like to say some words at the end, because instead of me, my colleague presented everything which was concerning our results and works on ACDRC and AI chip and so on. And thank you for your listening. And I would like to invite you to Prague, because I see a lot of students, and maybe it will be interesting for you, but not only for students. We will organize 15th realization of Prague Embedded System Workshop. I am general chair with my other colleague who is also interested in security and safety. And I would like to give you some invitations. You can come to Prague because it is PhD forum where there are also a contest of the best bachelor or master thesis. You can ask your colleagues, younger colleagues, which is sponsored by IEEE. And come to Prague and present something. We have several type of presentations. You can present something what was presented of some other conferences in a way. Sorry. For you. And we can realize such co-located actions which will be concerning this ACDRC or some solution of special work.
okay,
Thank you for this. And
okay, thanks a lot. Okay, so thanks to all colleagues from CTU Prague. So now we have closed the morning session, and if I may ask you before we leave for the lunch, which is already prepared behind the door, shall we make at least one group photo of the attendees and lecturers, possibly in front of this wall?